Okay, what are we doing today?
We're just taking a drive to the park. Rockbridge Museum or something. Furnace Museum. It's a furnace museum. We good over there?
No. I need a selfie stick.
Oh my god.
Oh my god. Like, Mike was saying some mind-blowing stuff yesterday, but the damn TV was blaring and I couldn't really...
It was blaring?
Yeah, because, like, when I played the video yesterday, I couldn't really, like, you can't really hear what you were saying. It was weird. Yeah.
Daddy, Lonnie has lipstick.
It was just...
No, Lonnie, I don't think you can have lipstick because you're too young.
She can have lipstick because Mommy said that she can have lipstick.
But she's only 5.
Don't matter.
Yeah,
I used to wear lipstick when I was 5 too.
What?
I used to wear lipstick when I was 5 too.
You did?
But I turned 5 years old and then I used lipstick.
You what? Oh, so Mommy used to wear lipstick when she was 5?
Yeah, my mom will only allow me to wear pink though.
Interesting. Yeah, before we do any check or something, we gotta call the
So,
people.
what was that? What's that term with the C? Coriolis? What'd you say? Coriolis effect?
Coriolis.
Coriolis effect.
Coriolis.
That thing is mind-blowing. That thing is mind-blowing. Basically, Mike was saying that, like if you throw something and your eyes, like, in some, what's it called?
Like objects in space or on Earth in the universe, they tend to follow a straight line, like a straight line path.
Mm.
You know, just at rest, like an object that's quote unquote at rest. But motion, the way we describe motion is based on a reference frame, or with respect to what? Like, how fast are you going? Are you moving with respect to what? With respect to this house or respect to the railroad? Anyway, so in an acceleration frame of reference, or around when you're going around rotating or accelerating frame of reference, if you throw an object or you let an object, release an object, free fall or whatever, it'll from your perspective, because you're on that accelerating frame of reference, or it'll appear to curve to the right or left or whatever. I forget what it is. But from I think an inertial point of view, which is from an inertial point of view, the object is going straight, and that Coriolis force, we think so from our point of view, on the accelerating or rotating frame, we see a curve and we're like, oh, there must be some kind of force that causes it to curve or whatever, and the force is the Coriolis force or whatever. And that force, Coriolis force, is not a real force, it's just our perception, but it's useful, for us to calculate things and describe how, things that we observe and stuff like that.
But you're saying it's really going straight, right?
Yes, it's really going straight. It's not curving. Because when you look at it from an inertial frame of,
So when you were driving and we just made that little curve right there, we're actually going straight. We're not going curve.
Well, yes. Well, let me think about it. Because when we're driving, right, it depends on, because there's inertial frame of reference, and then there's a non-inertial frame of reference. Oh, look at this tree. See, they trimmed it real nicely. So when you're driving, it depends, because if you're driving at a constant velocity, you're not accelerating. That's an inertial frame of reference. Okay? When you're accelerating, you're changing your velocity as time progresses, then that's a non-inertial frame of reference. But the driving thing is different. We're turning the wheels and this and that. I'm not talking about that.
You're talking about just really like something that's freely.
No, not right now.
Yeah, we don't have We don't have charge.
But you see, the thing is this. Okay, the Earth that we're on, right? It's a big rotating. Oh shit!
When you use my star code,
I think the Earth is not an inertial frame of reference.
Just 3 letters.
Yeah. But anyway, since the Earth is moving at such a large speed and we're part of that frame of reference on the Earth, we don't perceive that 1,000 miles per hour rotation around the Earth's axis or whatever. And also, we don't perceive the speed with which, or the velocity with which we're
Really simple.
orbiting the sun or even the galaxy, which is like crazy speeds.
It's crazy.
But because we're all moving with the Earth, I mean, we're all with the Earth at the same time, the air, the atmosphere, everything. So we're all going the same speed. So we can't perceive it because our frame of reference is the Earth. But if somebody else was on another planet or whatever, or, you know, they'll see us moving fast as fuck. You know what I'm saying?
Mm-hmm.
Yeah.
That's crazy as hell.
Yeah. And that I guess that was part of the theory of gravity, the relativity, general relativity. And Einstein even postulated further special relativity. Actually, special relativity came first. Time dilation. And this shit is crazy because the speed of light, according to Einstein, is constant. It never changes based on the observer. Whether you're standing there or driving or whatever, the speed of light is constant. So if somebody is moving faster than, basically, the faster you accelerate and approach the speed of light, right? The slower time runs for you. Your time clock slows down. Yeah.
That's crazy.
It is crazy, and it's kind of mind-boggling because yeah, because, and the thing is, because the speed of light doesn't change, it's constant according to, you know, Einstein's special theory of relativity. That is why GPS satellites that are orbiting way above the Earth in space or whatever, their clocks are a little bit slower than the clock, than the time on Earth. Like, the higher up you go, the slower time, you know, your time slows down. So they have to make that adjustment for GPS and stuff so that our clocks work here back on Earth. It's weird. You gotta let the experts describe it to you because it's kind of hard to describe.
Wow. That's amazing. Like, I love science now just because of you.
Because of me? Oh, well, I'm glad I could help.
And Elon Musk.
Elon Musk.
Yeah.
Are you going to our
But the thing
No,
with the
not the
Apple
church.
and stuff like that was kind of crazy.
I mean, it's all part of the
Say the Apple one again. Like the Apple, like that thing, like really like opened up my eyes.
It's like when an apple falls from a tree, or a mango falls from a tree or whatever, and we seeing it free fall. It's free fall. Einstein said free falling is the same here on Earth as it would be as somebody who was in space free falling. Like, you can't perceive that you're falling until you make contact. So basically, if an apple falls from a tree, did the gravity of the Earth pull it down so that it fell, or did the Earth accelerate up and catch up with the apple to make contact? Which is it? And according to the theory of you know, general relativity, the apple, you know, is the Earth that, you know, is accelerated up to meet the apple or the mango tree.
That's so crazy. I love that. I love hearing that one.
Yeah, that's cool. I don't know if I said it right, but